Hey, what's going on, everybody? This is Dan from Abbott University. I'm relaxing right now. It's a beautiful Sunday in Asbury Park, and I decided I wanted to do a video on rate, time, and distance problems. I find that when I'm tutoring students for the SAT math section, this is definitely one of the kinds of problems that students tend to have trouble with. So there's a way that I go about them that tends to work for me pretty consistently. And it always begins with me remembering that rate times distance, or times time rather, equals distance. And then what I do is, for rate, time, and distance problems, I almost always end up using this chart here that I'm drawing right now. And the chart is this big box that goes underneath the rate times time equals distance equation, and then I divide it up into 3 columns. Now, this column here represents the rate, or the speed, or usually it's the average speed of a moving object. This represents the time. For these problems, you tend to, or you need to be careful usually regarding what unit of time you're analyzing. It could be hours, it could be minutes, and so forth. And of course this column represents the distance, often in miles, at least in America. So those are the 3 columns, and then you have these 2 rows here, and the rows are for the moving object or objects. So let's say that the word problem features 2 moving objects. Well, the top row would represent the behavior of the first moving object, and the second row would represent the behavior of the second moving object. If you were analyzing only one object for a word problem that was featuring a single object that was perhaps moving at different speeds within the same kind of trip, maybe a trip there and back problem, well, this would represent the first part of the trip of the solo object, and this would represent the second part of the trip. So I think that makes sense, probably. I say we dive right into some examples just to see how to use this chart on here. Alright, so here's the first problem. Train A leaves Asbury Park for Red Bank at 40 miles per hour. 2 hours later, Train B leaves Asbury Park for Red Bank at 60 miles per hour. How long will it be before Train B overtakes Train A? Alright, so right off the bat, we know that we're dealing with Train A and Train B. So I'm going to go ahead and write that in this section here, where the first row of this table, or chart, I'll call it a table. I think it's a table, actually. First row represents the activity of Train A. Second row represents the activity of Train B. So now that that's done, we're going to move on. Looks like we lost the problem here. There we go. Alright, before we start filling in more information into that table there, I also think it's often a good idea to make another really quick diagram that helps you visualize what's actually happening here. Now what's happening is we have Train A leaving from a particular city towards another city. So just to represent that, we've got A over here, and we've got an arrow representing the fact that it's going in a particular direction. Now, Train B leaves the exact same city, so I'm going to write that directly underneath Train A to signify the fact that it's leaving from the same city. And not only that, it's traveling in the same direction. And furthermore, if you notice, the length of the arrows are the same, and that represents the fact that in the end, the total distance traveled by each train will be the same. Because Train B leaves the same city 2 hours later, it's moving faster than Train A, and then at a certain point, it overtakes Train A, and in that very moment where it overtakes Train A, both trains will have traveled the exact same distance. Very good. So that's a nice way of getting a handle on what's actually happening in this particular problem. So here's the point where it's a good idea to fill in that table. So what do we've got? We've got train A leaving Asbury Park for Red Bank at 40 miles per hour. So that means that train A is traveling 40 miles per hour. And we've got train B leaving Asbury Park for Red Bank at 60 miles per hour. So that means train B is traveling at 60 miles per hour. I'm going to go ahead and fill that part in now. Alright, so train A 40 miles per hour and train B 60 miles per hour. Now, we could also start filling in that time column here. But before we do so, I'd like to get very clear about what is the unknown that we're trying to solve for. Often it's a good idea to analyze the very question of the word problem to find out what the actual unknown is. Now, what they're asking ultimately is how long will it be before train B overtakes train A? So another way of phrasing that is how many hours on the train tracks was train B? So how long was train B traveling? Because it left 2 hours later, and then it's on the train tracks, heading towards Red Bank, then at a certain point it overtakes train A. So how long did that take? So in other words, the unknown is the time traveled by train B. So we're going to call that X. If the unknown, or if the time spent on the train tracks by train B is called X, then when we're analyzing what time to place here for train A, we have to recognize the fact that train B left 2 hours later. So that means that train A has been on the train tracks traveling for 2 hours more than train B. Reminding ourselves that train B has traveled for X hours, well, that means that train A must have traveled for X plus 2 hours. So we're going to write that right now. Very good. So we've got that information filled in. Of course, the question is, where do we go from here? Well, I find it personally helpful to just fill in the rest of the chart. I mean, even if you don't know what to do next necessarily, whether or not to use algebra or whatever, it's helpful often to just fill in the rest of the chart, because even if you don't know what to do, just when you see the information laid out, it might trigger some insight regarding the next step of the process. So we're going to fill in the rest of the chart. Now, do we know the distance traveled by each of these? Not really. We don't know how much distance train A went and train B went. We know that the distance is the same, however. Nonetheless, let's fill in that part of the table. So over here, we might not know the exact distance numerically, but we know how to represent it algebraically. And the way to represent it algebraically is to recognize that train A traveled 40 miles per hour for X plus 2 hours. So total distance traveled by train A, guess what? It's going to be 40 times X plus 2. Now, I'm going to assume that the viewer knows how to use the distributive property and would know, therefore, that the product of 40 and X plus 2 is 40X plus 80. I'm going to go ahead and write that in this space here. A little bit of a tight space. Good. And train B traveled 60 miles per hour for X hours. Therefore, train B has traveled 60X miles. And as you may recall, we know that the distance traveled by both of these trains is the same ultimately. So that means that this 40x plus 80 is equal to this 60x right here. That's very helpful information because at this point it's clear we can solve for x. And the way that we can solve for x is by setting up an algebraic equation. And that equation would be 40x plus 80 equals 60x. Okay. I think a lot of students are used to having all the x's on the left-hand side of the equal sign and all the other stuff on the right-hand side of the equal sign. I don't care about that. I don't mind whether x ends up on the left-hand side of the equal sign or the right-hand side of the equal sign. For some reason, I like to just keep the x terms positive whenever I can because I hate dealing with negative numbers, to be honest. So what I'm going to do from this point is I'm going to subtract 40x from both sides. Obviously, that would lead these to cancel out. You'd have 80 equals 20x. And at that point, it would be a matter of dividing both sides by 20 in order to solve for x. These would cancel, leaving us with x equals 4. So what that means is train B traveled 4 hours before it overtook train A. Awesome. Alright, so here's the second problem or the kind of problem that you could be facing. A car leaves New York City for LA traveling at an average speed of 70 miles per hour. At the same time, another car leaves LA for NYC traveling 60 miles per hour. If it is 520 miles between New York City and LA, it's definitely not, by the way, how long before the two cars meet, assuming that each maintains its average speed? Okay, now the cars here are not labeled, so I'm just going to call it, similar to the last problem we did train A, train B, we'll just call it car A and car B. So, similar to last time, again, just to fill that part in. A and B. And we're going to do that diagram again that represents the directionality and the distance traveled by car A and car B. This time, it's a little bit different because car A left from New York City towards LA, and car B left from LA towards New York City. So I'll try to keep the whole kind of east-west orientation going here. So here's car A, and it's traveling west, and then car B is in LA, and it's traveling east. And at a certain point, they meet. Okay, now, let's see. Car A travels at 70 miles per hour, and car B travels at 60 miles per hour. So, you know what that makes me think? Let's just have car A, the arrow emitting out of it, it's going to be a little bit longer than the one emitting out of car B. And the reason for that is I want to make sure that it's clear to me that car A actually traveled a longer distance because car A is moving faster. So by the time that the two cars meet, car A will have traveled a longer distance. Okay, so moving on to the chart. Let's see, car A leaving from New York City towards LA travels at a speed of 70 miles per hour, so we can go ahead and fill that part in. Over here, so that's 70 miles per hour. I like to put that line through the 7 just to make it so that I'm very clear that it's not a 1 that I just wrote. And car B travels at 60 miles per hour, so we can go ahead and write that part too. Alright, and it's 520 miles between New York City and LA. So how long before the two cars meet? So the time traveled by both of these cars is the same if you think about it. I mean, car A was driving, and car B left at the same time, so that car is driving, and then they eventually meet, hopefully not a head-on collision, maybe they just pass each other. In that moment, nonetheless, they will have both traveled for the same amount of time, because they both left their corresponding city at the same amount of time. And the problem is asking for, well, what is that time? So that's the unknown. We're going to call that time X. So, car A, how long was car A on the road? It was on the road for X hours. How long was car B on the road? Car B was on the road for X hours also. So, ultimately, we're probably going to have to use algebra to solve for X. Just like I mentioned last time, probably a good idea to fill in the rest of the table. It usually is. And at this point, we could fill in the row for car A right here, or this cell right here. Now, we don't know how long car A traveled at this point yet, numerically, but one thing we do know for sure is it traveled 70 miles per hour for X hours. So since rate times time equals distance, we know that car A traveled 70x miles. Car B similarly traveled 60x miles for the exact same reason. And the question is, of course, what do you do from here? This problem is significantly different from the last one, which is the reason why I put it up here. If you notice in the actual body of the word problem, there's mention that there are 520 miles between New York City and LA. So what that means is, whatever this distance is, this arrow, plus this arrow, you know that when you add them up, you're going to get 520 miles. So there's 520 miles between these two starting points right here. So how does that translate algebraically? Well, that means that this distance that car A traveled plus the distance that car B traveled is going to equal 520 miles. So already that gives us a glimpse into the algebra equation that we need to write in order to solve for X, because once again, our ultimate goal is to just simply solve for X. We've set it up that way. So 70x, I'm going to make this a little bit thicker. So 70x plus 60x equals 520 miles. And we've got some like terms on our hands. We've got the 70x plus the 60x, so we could combine those, which is always a good idea in algebra. You simplify both sides of the equation first before you do anything else, and we can simplify the left-hand side by combining these. We've got 70x plus 60x, so that equals 130x. So 130x equals 520. Great. And to solve for x, we've got to, in a sense, get rid of this 130, so x is all by itself on the left-hand side of the equal sign. We can do so by dividing both sides by 130. Now, some of you might be able to do that in your head. I actually am not the best at doing stuff in my head. It's good to use a calculator, but I could do this one in my head. I know that 520 divided by 130 is 4, actually. So we've got x equals 4 hours, so it happens to be the same answer as the last problem. So 4 hours is how much time it took before the two cars met. Alrighty, so here's the third problem. Two planes leave Kentucky at 10 a.m. One heading for Africa at 600 miles per hour, the other one heading in the opposite direction at 150 miles per hour. At what time will they be 900 miles apart, and how far has each plane traveled? Well, right off the bat, you might notice this problem's a little different in at least two different ways. One of them is the fact that there are two questions to answer, so just make a mental note of that to make sure that you're thorough answering both questions. Also, another thing is, this is the first time that we're dealing with clock time. We've got clock time of 10 a.m. over here, and notice that they're not asking like how long were they flying. The question is, at what time will they be 900 miles apart? So you should think in your mind that we'll probably have to find out how long they traveled, how many hours they traveled, and then we're going to have to end up adding it to this 10 a.m. to get this clock time, to find out what time they end up at 900 miles apart. So, moving on. We've got one plane leaving Kentucky at 10 a.m. We're going to call that plane A. We're just going to stick with that. We've got plane A and plane B. So we're going to do the exact same thing that we've been doing here. Plane A over here and plane B. And now we're going to move into the diagram drawing. This one's a little bit different because it's two planes leaving the same location, but they're traveling in different directions. Now, since they're leaving the same location, I'm going to represent that location as like this circle right here. Okay? And we've got plane A leaving that circle and heading from Kentucky towards Africa. So plane A is heading east. So how that will translate visually is I'm going to draw this nice little divider right here. And plane A is leaving Kentucky, heading east. Bam. Plane B is leaving Kentucky, heading in the opposite direction according to the problem. Now I'd like you to notice a couple things. First of all, plane A rather, traveling east, is moving at 600 miles per hour, and plane B, heading west, is traveling at 150 miles per hour. So that's why I made the arrow of plane B significantly less than the arrow of plane A, because at a certain point, these two planes will have traveled 900 miles, or there'll be 900 miles apart, I could say. They're going to be 900 miles apart, so there at a certain point will be a distance of 900 miles between the two arrow tips here. And by the time that happens, plane B will have traveled less distance than plane A, because plane B is moving slower. Plane B is only moving at 150 miles per hour, and plane A is moving at 600 miles per hour. Okay. So let's fill in the table as best we can with the given information. So once again, analyzing plane A. Now once again, it's kind of tough because the word problem didn't say plane A and plane B. That's something that we had to do for ourselves. We actually had to label that ourselves. But just keep in mind that plane A is the first plane that we're analyzing. So plane A leaves at 10 a.m. We're not going to worry about that part just yet. It's heading for Africa at 600 miles per hour. So that's immediately a clue. Like we could definitely fill in the 600 miles per hour underneath the rate of plane A. So that's 600 right here. And plane B is traveling in the opposite direction at 150 miles per hour. So that goes right here. Now, once again, ultimately, the problem is dealing with at what time they will be 900 miles apart. In other words, at what time will this situation occur? And we don't know yet, obviously. That's ultimately the answer, but probably a good idea to find out, well, okay, well, how much time were these planes flying in the air? You know, how many hours were spent flying in the air? Because, once again, once we find out how many hours they were flying in the air, we could just simply add that to 10 a.m. and find out the clock time answer to this question. So we could at least temporarily treat the unknown, or we could temporarily treat the time that these planes spent flying in the air as the unknown. So we're going to once again call that x. So we've got x over here. And guess what? Plane A traveled for X hours, but so did plane B, right? Because they both left at the same time, right? And they traveled in opposite directions. At a certain point, there's going to be 900 miles between them, and in that moment, in that very moment, they will have both been flying in the air for the same amount of time. So it's safe to put X here and here. Very good. So once again, even if you don't know the proper path to take from this point forward, still usually a good idea to fill in the rest of the chart. I'm going to do that right now. We've got a distance of 600x for similar reasons as what we've been working with before. So we've got 600x right here. And we've got 150x right here. Now, I'm sure some of you at home are already guessing what the proper algebraic equation would be to solve for x. And you're probably right. We know that this represents the distance traveled by train A, and this represents the distance traveled by train B, or plane B rather, we're dealing with planes. And we know that this distance plus this distance equals 900, so we could use that information. So that's why this diagram is really, really helpful. You kind of visualize exactly what's going on. So in other words, we know that 600x plus 150x equals 900. So let's go ahead and write that. 600x plus 150x equals 900. Now there is an opportunity to simplify the left-hand side of the equal sign here. 600x plus 150x, that equals 750x. It still equals 900. And to solve for x, it would be a matter of dividing both sides by 750, which would leave us with x equals 1 1/5. Now, that is 1 1/5 hours. So that could be a little bit confusing because, okay, it's like 1 1/5 hours. What is that? You know, it's definitely at least 1 hour, but what's 1/5 of an hour? Well, 1/5 of an hour happens to be 12 minutes. One way of finding that out is to kind of go off to the side. If you don't have conviction about that, you can go off to the side and just be like 1/5 times 60 minutes. And you may notice that what's really going on there is it's a direct algebraic translation of the verbal question. The verbal question is, what is 1/5 of 60 minutes, of an hour? 1/5 of, the word of usually means multiply, and then 60 is just 60, because it's 60 minutes. We're converting into minutes. Now 1/5 times 60 is 12. Okay, I'm going to assume that the viewer knows how to multiply fractions and whole numbers. So we've got 12 over here. So in other words, this 1 1/5 hours is really 1 hour and 12 minutes. So just to make things easy for us, I'm going to write that right here. So we've got 1 hour and 12 minutes. You know what? I'm going to bring another color into the video. Yeah, baby. 1 hour and 12 minutes. Now, remember, the word problem is not asking for how long were the planes flying in the air. The word problem is asking for what time will they be 900 miles apart. So here it is. I'm going to blow this up a little bit. At what time will they be 900 miles apart? Well, we know that they left at 10 a.m. and they know that they've been flying through the air for an hour and 12 minutes, right? So that will be 1 hour plus 10 a.m. That's 11 plus an extra 12 minutes. We're looking at the clock time answer of whatever. You know what? I'll leave it in blue. 11:12, and that's a.m. actually. So that is the answer right there. To the first question, but remember there's another question that we have to answer, and that is, how far has each traveled? Well, how can we find that out? How far has each traveled? Well, the distance that each of these planes traveled is represented here, isn't it? So we've got plane A traveling for 600x distance. We got plane B traveling for 150x distance. Now remember, we already know what x is. We already solved for it. X is 1 1/5 hours. I think at this point it's probably a good idea to convert this 1 1/5 to an improper fraction. Now that does indeed equal 6/5. I made brief mention of that before. So 1 1/5 equals 6/5. So that means that this x right here is 6/5. So in other words, this x right here is 6/5. So if I want to know how much distance plane A traveled, all I got to do is multiply this 600 by 6/5. I'm going to do that. Now that's something that I can do off to the side. I like to, this might not be the best thing to do, but I like to actually get kind of creative about where I solve the problems. I'm going to draw this little barrier right here for this second part. So it's kind of like the final stretch of solving this entire problem here. So once again, that x is 6/5. So in order to find this distance here, it's got to be 600 times 6/5. So I'll just go ahead and write that. Instead of drawing the times symbol, I'm just going to draw 600 with parentheses 6/5 right here. Now, what does that equal? Well, that would end up being 720 miles. And we could, there's actually a couple things we could do here, but let's just keep it simple. And we'll stick with the same process here. We've got 150x. Again, the x is 6/5, so if we want to know how much distance plane B traveled, we'll be 150 times 6/5 for the exact same reason. So we go ahead and do that. 150 times 6/5, and that would equal 180. Now, in case you're not so sure whether or not your answers are correct, one thing you could do is you could add that 720 miles here plus this 180 miles, and that should equal the total distance between the two planes in that point. That's 900 miles between them. Okay, so that's that problem. I think it's the third problem. Moving on to the next. All right, next problem. You make a business trip from your house to South Beach, which sounds like an amazing business trip, and you get there in 2 hours. 1 hour later, you return home at a rate of 20 miles per hour less than your rate going there. If you are gone a total of 6 hours, how fast did you travel on each leg of the trip? Okay, well, right off the bat, this is a classic trip there and back problems. That's kind of a subset of these time, rate, and distance problems. It's a trip there and back where it's like you leave from home and then you come back. Okay, so that's one thing to notice. There's really only one moving object, and that's you. That's you in your car. There's not two planes that we're dealing with. There's not two trains that we're dealing with. We're dealing with you in your car. So what that means for us is, instead of labeling the like train A over here and train B over here, we could call this section over here trip 1. Or we call it like there. Let's do it like that. We'll call it there. Okay. This is us traveling there. In this case, it's South Beach. And this row represents us traveling back home from South Beach. So we could get that part over with. And then from there, getting that visual diagram going, let's say, alright, so you got, let's say this is your home. You know what, why not? I'm gonna make it look like a house. Why not? So here's your home. Yay. Looks like an arrow, but it's a house. That's your home, and you travel to South Beach. I'm going to draw a palm tree. Alright, South Beach, Miami there, with the sun shining. Nice. And, you go all the way there. We don't know how fast you were going, okay? We don't really know much information at all, other than the fact that you left your home and you went to South Beach. But then, you travel from South Beach and you go back home. Okay, and notice that the lengths of the arrows are the same, and the reason for that is because the distance there is the same as the distance back. That should make perfect sense to you. Looking at the problem here, let's see. You make that first business trip from your house to South Beach in 2 hours. Okay, well that's good. That 2 hours right there, that gives us some information that we can fill in right there. Like it took you 2 hours to get from your home to South Beach. So I'm going to fill that into that cell right there. That gets a 2 for 2 hours. 1 hour later, you return home at a rate of 20 miles per hour less than your rate going. Okay, and you're gone a total of 6 hours. How fast did you travel on each leg of the trip? Alright, well this is kind of a tricky one because it's like, how fast did you travel on each leg of the trip? You had a certain speed going there and you had a certain speed going back, right? And now these speeds are different too, right? So unlike some of the previous problems, we don't have a single variable to solve for. This is almost like the last problem where there's kind of two questions embedded in there. It's like, how fast were you going on this trip? And how fast were you going on this trip? Well, it doesn't really matter what we assign x to. We're just going to assign the x to the speed that it took to travel there, that you used to travel there. So we're going to call that x. Now, this speed that you used to travel back is 20 miles per hour less than that x. So we could be like x minus 20 right there. And keeping in mind what the ultimate goal is, the ultimate goal, once again, is to find out what x is for sure, but then we also want to find out what x minus 20 is. There are, once again, two answers to this problem. Obviously, a good first step is to find out what x is first, because once you know that, you can just subtract 20 from it to find the other value. Alright, now here's where you have to be kind of careful because they have some sneaky stuff going on in this word problem where, it says like you're gone for a total of 6 hours. Well, in that moment, just by saying you're gone for a total of 6 hours, it might be tempting to be like, alright, well it took you 2 hours to get there, so if you're gone for a total of 6 hours, then it must have taken you 4 hours to come back, right? That would be pretty intelligent. But the problem is, they say that 1 hour later, so you were actually hanging out in South Beach, rightfully so, and understandably so, for at least an hour, which really isn't that much time. But you were there for an hour, okay, and then you went back. So this trip took you 2 hours, you hung out for an hour, and then you went back. So that means, and you were gone for a total of 6 hours. So that means that since you hung out for an hour here, that means that instead of putting a 4 in this position, we're going to have to put a 3 in this position. So the total travel time was actually 5 hours, right? Because you were gone for a total of 6 hours, but that 6 hours includes the hour that you spent over here, chilling. Alright, so that's why you have to be careful. You got to put a 3 there, not a 4. Now, as was the case with many of the previous problems, the distance traveled with the two arrows is the same. So the arrows are the same length, symbolizing the fact that the distance was the same. Alright, so that's going to be helpful when we actually bring in the algebra into the process. So let's fill in the rest of the table. We've got 2 times x, or x times 2, also known as 2x. And we've got x minus 20 times 3, once again using the distributive property. that would give us a 3x minus 60. So just going to see if I can get some thinner ink here. We've got 3x minus 60. Very good. So we also know, judging by the arrows over here, that the distances are the same. They're actually equal to each other. So we could represent that very fact algebraically by creating this equation where 2x equals 3x minus 60. Alrighty. What we'll do from here is we'll subtract this 3x from both sides. We'll have all the x's on the left-hand side of the equal sign. So we've got minus 3x, minus 3x. So already we're going to have some annoying negatives. I typically don't like that, as I mentioned before, but whatever. We're going to have the x's on the left-hand side. So we got 2x minus 3x. That's going to be negative x, negative 1x. We could just write negative x, and that equals negative 60. And that's easy enough. Dividing both sides by that invisible negative 1 there. Canceling that out leaves us with x equals 60. So very good. X is 60, so that means that we went 60 miles per hour there. Once again, the problem is not only asking for that particular speed, it's asking for this particular speed as well. And as many of you can see, that would be 40, seeing as how this x is 60 minus this 20. Just to be thorough, I'm going to write that, even though I've just verbalized it. So x minus 20 is 40. So what are our answers? These are our answers. 60 miles per hour there, 40 miles per hour back. Alright, so final problem for this particular video about rate, time, and distance problem. Okay, so what is the problem? Jerry and Maurice go on a camping trip with their unicycles. One day, Jerry left camp on his unicycle to go to the Shrewsbury Grove. 10 minutes later, Maurice decides to go too. He's like, hey, I want to go to Lululemon too. If Jerry was traveling 30 miles per hour and Maurice traveled 35 miles per hour, how long was it before Maurice caught up with Jerry? Alright. Okay, so, well, first of all, this is the first problem on this particular video where we're actually dealing with names instead of like, well, and people, well, not necessarily people, but we're dealing with names. Instead of like train A and train B, blah, 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 we're dealing with Jerry and Maurice. So, we could represent Jerry as a G and Maurice as an M. So let's go ahead and do that right now. G. You know, I want that to be a little thicker actually. Alright, so we've got G over here. And we've got M over here. And as we've done before, we're going to get that visual diagram going over here. Well, they're both camping, and then, you know, they both go to the Shrewsbury Grove. So they're both, you know, leaving from the very same origin. And what we could do is represent Jerry's journey first. So here he is, G, and he's camping, and then he goes this way. Okay, now we'll just assume that the Shrewsbury Grove is over here. When I say over here, I guess you can't see it. Over here is what I mean. And he goes in that direction, and Maurice goes in the same direction, although he does leave 10 minutes later, according to the problem. Once again, the lengths of the arrows are the same, and that is because this is another problem, just like the first problem in this video, where Maurice is traveling faster than Jerry. He leaves 10 minutes later, and he's traveling faster, so there's at a certain point, he catches up, caught up with Jerry, catches up with Jerry, and in that moment where he catches up with Jerry, in that very moment, they will have traveled the exact same distance. So we represent that fact with arrows of the same length. Okay, so what do we do from here? Well, I am already noticing embedded in this word problem there's two speeds. There's 30 miles per hour and 35 miles per hour. 30 miles per hour represents Jerry's speed. So I'm going to fill that in the table right now. 30. And Maurice traveled this 35 miles per hour, so we can also represent that. Good. All right. Let's see. Well, paying attention to the ultimate question that they're asking for, they're saying how long was it before Maurice caught up with Jerry? So another way of phrasing that is, how long was Maurice on the road, on his unicycle? Okay, now I can understand that that is what is so often difficult about word problems, because it's like, well, how do you interpret it that way? Well, just remember that 10 minutes later, Maurice decides to go also. Alright, so they just finished mentioning that part of it. And then they move into the question, how long was it before Maurice caught up with Jerry? So in other words, after Maurice left, from that point forward, how long was it before he caught up with Jerry? So in other words, the unknown, value that we're trying to figure out is how much time Maurice spent on the road. Now, as far as this table goes, that's represented in this cell right here. So since that's the unknown, since that's what we want to find out, we're going to represent that with a variable. Now we've been using x, we're going to get crazy and use an a because I'm actually bored with the x. So we've got an a right there, and once we find out what a is, we are done with this problem. Let's take a look. Do we know how much time Jerry spent on the road? Well, let's see. Jerry definitely, he's been on the road for a while. He's definitely been on the road longer than Maurice has, because he started first. So he's definitely been on the road at least 8 hours. But he's been on the road longer than Maurice. How much longer? 10 minutes longer, because Maurice left 10 minutes later. So that means that Jerry has been on the road for the exact same time as Maurice, only we can add on 10 minutes. Now, you have to be very, very careful, because this says 10 minutes. This represents, this is speaking to units of time in minutes, whereas this column on our table is representing hours as the units of time that we're analyzing. So you cannot just write a plus 10 over here, because what that would be interpreted through the table as, it would be a plus 10 hours. Now clearly Maurice did not leave 10 hours later. So we have to figure out what fraction of a total hour is 10 minutes. Well, that's really not too difficult. Imagine that this entire circle represented a total hour, also known as 60 minutes, and this represented 10 minutes. Okay, so what fraction of the entire circle is this sector that represents 10 minutes? Well, that would be 10 over 60, also known as 1/6. So 10 minutes is 1/6 of an hour. So that means that instead of writing a plus 10 over here, which would unfortunately and mistakenly imply that Jerry traveled for a plus 10 hours, we would write a plus 1/6. Very good. So that's what we've got so far. Once again, we might not know what to do from here, but we could always fill in the rest of the table. So doing so, on the top row, using the distributive property, we would have 30a plus 30 times 1/6. 1/6. So that would be Now 30 times 1/6, that is 5, if you were to do the math. And then on this bottom row, we have just 35 times A, so we've got 35A. Alrighty. Now, similar to many of the other problems, the distance traveled by both of them was the same. So that means that this distance right here equals this distance right here. So let's set up an algebra equation that enables us to solve for A. That would be 30A plus 5 equals 35A. Alright, in my attempt to keep the terms that have the variable in it positive, I'm going to subtract 30A from both sides. You don't have to do that. I just like to do that. We end up with 5 equals 5A. Alrighty, dividing both sides by 5 gives us A equals 1. Alright, so A equals 1, and what we're dealing with specifically is hours. So that means that A is 1 hour. Right there. Let's return to the problem and make sure that we've actually solved it. How long was it before Maurice caught up with Jerry? Yes, very good. It would be 1 hour before Maurice catches up with Jerry. So that concludes the video on rate, time, and distance problems. I hope that was helpful. And stay tuned for the next one. Also, check out the website if you can, abbottu.com. Alright, I'll talk to you later. Bye.